Hello students, welcome back. As an optional lesson, let's do some advanced algebra. We already know what a polynomial is, what is degree, and what do you mean by the division algorithm. Well, let's talk about the division algorithm just a little bit. Here we go. Divide polynomial f of x by polynomial g of x, then you can write f of x as q of x times g of x plus r of x, where the polynomial q is the quotient and polynomial r is the remainder. And this is important. The degree of the remainder is strictly less than the degree of the divisor g of x. That's the division algorithm. All right. Now the next topic is so-called the remainder theorem. Let f of x be a polynomial, then the remainder of the polynomial division, f of x divided by x minus c, is just f of c. So remainder is constant, and that's easy to see because divisor has degree 1. So the degree of the remainder has to be less than that. So the remainder has to have degree 0, so this has to be a constant, just a real number. And that real number has to be f of c. The proof is actually pretty simple. Put it into this division algorithm. Instead of this remainder here, r of x, we have just r for the same reason we just talked about. This has degree 1, so this has to be degree 0. So it's just r, the real number. And then here, plug in x equal to c. Then f of c is c minus c times q of c, that's 0. So what do we have? F of c is equal to r. And that's it. I said sketch of proof, but actually this is a full proof. So remainder theorem, just f of c, that's the remainder. Now, the factor theorem is a special case when the remainder is 0. Then remainder is 0, then x minus c is a factor. So the sketch of proof goes like this. F of c is equal to 0. What do you mean by that? The remainder is equal to 0. And that means x minus c is a factor. Okay. All right. Factor theorem. Now, how do we use this factor theorem? Factor the given polynomial. Okay, all right. How do we factor a given polynomial? And this is cubic polynomial. Now, if you have a cubic polynomial or even quadratic, I usually recommend students to do factor by grouping first. Trial and error, various method, and try to factor by grouping and make it work. Factor theorem is actually the last resort. All right, let's suppose that everything failed and we have to use the factor theorem. Okay. Rotten luck, here we go. Where do we start? We start from the constant term and the leading term. If the leading term is 1, monic, it's a good news. Things are much easier. But in this case, rotten luck twice. It's not monic, it's non-monic, so we have to consider something more complicated. Okay, let's list all the potential zeros. Basically, what we need is factors of the constant term is going to be the numerator, and the factors of the leading coefficient is the denominator, and numerator of the denominator, we have this long list of possible zeros. So this one has factor 1, 2, 3, or 6, and plus or minus, of course. And this one has factor 1 or 2, plus or minus. And then take the ratio. If the denominator is 1, then you get 1, 2, 3, 6. There you go, and always plus or minus one way or the other. And the denominator is 2, then 1 over 2, 1/2. 2 over 2 is 1, that's already covered. 3 over 2, that's 3/2. 6 over 2 is 3, and that's already covered. In the end, we have all these. As for the reason why we have to consider the factor of this over factor of that, here is the reason actually. If f of p over q is 0, that means qx minus p is a factor. Alright? And then we have something there. And then if you break it apart, how do you get the leading coefficient? You get by q times a. Q times a is 2. So this q has to be a factor of the leading coefficient 2. That's where the denominator is coming into play. Now, how do you get the constant? This is minus p times c. This constant and that constant. So that is equal to -6. So the conclusion, this p must be a factor of the constant term. And that's why we have the first line. So this over that, and we have this potential zeros here. Okay, all right. Now check each candidate. Plug in x equals to 1 and check if it is 0. If it is 0, great. X minus 1 is a factor. If it doesn't, then plug in x equal to -1. Plug it in. If it is 0, great. X plus 1 is factor. And then if it doesn't work, try this integer, try that integer. If everything fails, then try fractions. But luckily, in this case, the first one, x equals to 1, the very first one, very simplest one, worked out fine. So up to here, I thought this was really triple rotten luck, really complicated, but I feel better now. After plugging in x equals to 1, in my first try, the very simplest, it worked out. So f of x is x minus 1 times its quotient. So how do you find this polynomial here? You can do it by polynomial division. You can do it by long division, or you can do it by a synthetic division. Here, the textbook author used the synthetic division here. I prefer to use long division, as a matter of fact. I never studied synthetic division, to tell the truth. I don't find it useful. Anyway, we got a factor. And then as for this factor, we have quadratic here, so try to factor it further. Now, if you start with quartic or quintic, after this, you're going to get still cubic or even quartic or something like that. If you start from original 6th degree, then even after this factor theorem, you're still down to 5th degree. After another factor theorem, we are down to 4th degree and so on. But we are starting from the 3rd degree here. So after only one factor theorem, we got quadratic. And quadratic is much easier to deal with. You can factor it further, and there you go. So there goes the full factorization. So factor theorem can be useful, but as I said, this is a last resort. Try to use factor grouping or everything first. And of course, the factor theorem, those kind of methods are really old methods. In 1970s, maybe, people used to study those a lot because they didn't have a lot of computing power there. But nowadays, you have computer algebra system. Let me show you. Let's go to a web browser here. And then let's go to Wolfram Alpha. wolframalpha.com. And then let's use this mathematical command, factor command, and then type in the polynomial 2x to the third power plus 11x squared minus 7x minus 6. And then let it run. And of course, we got the same answer as before. Now, which method do you prefer? I prefer the second method infinitely more, but of course, you have to have a certain proficiency on computer algebra system. In 21st century, this kind of thing is required. So you gotta learn how to deal with computer algebra system. You gotta know some commands. You gotta able to use some computer algebra system. Wolfram Alpha is a good one because it's free, but if you're doing something more serious, then you may need to use Wolfram Mathematica or something different too. Anyway, this is required. At least in my opinion, everybody should be able to do it this way. If you can't, then you gotta learn it to do it this way. But then again, come on, what do you prefer? So each time I encounter a student who shows some frustration or some resistance on learning computer algebra system, I point them toward something like this. Okay, if you don't like to do it with computer, do it by paper and pencil method. See if you still want to avoid computer. I show this to many people and nobody disagreed with me. Okay, we have a little bit of time left, so let's go to multiplicity theorem. So previously we had factor theorem. X minus c is a factor. But in this case, I don't know anything about q of x here. Multiplicity theorem says if q of x has any x minus c factor there, then keep getting it out and until you completely run out of x minus c factor, and then in the end, q of c should be non-zero. So that's the multiplicity theorem. How do you prove it? Actually, it's a repeated use of the factor theorem. So you can write like this, all right, x minus c times q1. And if q1 of c is 0, then we are through. We're already there. Q1 of c is 0, then Q1 of x is divisible by x minus c because of that factor theorem. So Q1 of x can be written as x minus c times q2. So plug that in place of here, then you have x minus c squared times q2. All right, now if q2 of c is not 0, then we are through. We are done. If not, do it again. q2 must be x minus c times q3, and plug it in right here, then we have x minus c third power times q3. And q3 of c is 0, then we are finally done. If not, do it again until we run out of all the powers. This process must stop because this degree cannot exceed the degree of f. So at some point it must end, and you're going to get a certain multiplicity. That's the full proof. And then if you complete it to all powers, then you're going to get all those linear powers associated to the zeros and multiplities m1 through mr, and then quadratic irreducibles. And why quadratic? That's related to something called the fundamental theorem of algebra. And in complex number field, everything can be factored completely all the way down to linear factors. But then again, if you have real polynomials, then you have to have complex conjugate. So 1, and then we have conjugate. So add them together, multiply them together, then we have the quadratic irreducibles. The detail is way above our heads, so let's stop here.